It's a pleasure to have Marco Zambón here with us today, who is going to tell us about multisymplectic observables and higher Courant algebra.
Thank you, Carlos, for the introduction. Thank you to Carlos, Mario, Roberto for the invitation. For me, it's especially nice to be here because I used to work here 2 years ago. It's like going back home. So I will talk about a joint project with one of my former PhD students. So let me write the title, even though Carlos mentioned it. Multisymplectic observables. And higher Courant. So this is the work I did with Antonio Miti, who's now finishing his 1-year postdoc at Max Planck. So, okay, I should apologize maybe because there will be no generalized complex structures appearing explicitly.
In interaction, everything is in interaction.
Okay. So there will be symplectic structures appearing, there will be Courant algebroids appearing. That's great. And I will start from the symplectic case because that's the easier to understand. And well, along the way, I will say actually where I'm going, what the goal is. Case. So let's take the symplectic manifold and omega. There are, well, at least 2 algebraic objects you can associate with. On the algebra functions, smooth functions, we have some bracket, which completely encodes the symplectic structure. Well, this is a Poisson algebra of observables. So in particular, it's a Lie algebra. So I will not care about the multiplication here. And something that you can associate is the following. So I assume that most of you know what a Lie algebroid is, but I will describe them in features anyway. So you can associate a Lie algebroid. So the underlying vector bundle is the tangent bundle plus trivial quadrat R, the trivial line bundle, and it has the bracket. The bracket that encodes somehow form. Say what kind of thing this is. So XF is a section here, so a vector field and a function. So if you give me 2 sections, then I define the bracket to be on the vector field part, there's the usual bracket of vector fields. On the function part, where we take the derivatives of the functions, and then we add the term which involves the symplectic form, reflecting the vector fields. Maybe I'll continue here. What is the main theme of the talk would be what is the relation between these 2 kind of objects, A and B. So in practice case, but there is a clear relation. There exists a Lie algebra morphism, a Lie algebra map, which is actually an embedding. It's called psi sub omega because it is an omega. So I'll put a little omega here to denote, to remind you that the some brackets the one come from omega. So there is a map, an embedding, an injective map like this, which takes a function and maps it just to the pair given by the function in a certain component and its Hamiltonian vector field with respect to omega, of course, in the first component. And so yeah, thanks to the fact that the bracket here is twisted by omega, this turns out to be a Lie algebra morphism. It preserves brackets. Okay. And so what I want to present in this talk is an extension to this of these 2 higher differential forms. So not only 2 forms, but 3 forms, 4 forms.
Are you going to talk about integration or not?
No, there will be no integration. So, okay. So I will also give some kind of geometric interpretation of this map. But first, let me make a remark. And this remark is actually not essential for the rest of the talk, but well, it's a property that this map has. So it's take me a couple of minutes to get to the main point. But so let's suppose that we have a Hamiltonian action of a Lie group. So G is a Lie group, a Hamiltonian action on our manifold. I will continue here. So with moment map. So the kind of symmetries you consider in symplectic geometry. Moment map to the dual. So that's a classical thing. Okay. Now let's twist this the following way. So I take the one form, which is G invariant. And so if the group G is compact, for example, I can take any one form and average it. So to get the invariant one. So I can twist the whole picture by this one form. So now twist the symplectic form by alpha, just by adding the alpha. If alpha is small enough, this will still be non-degenerate. So of course, this is in the same cohomology class as omega. And so the action will still have a moment map. So with moment map, let me just write a symbol for it, J alpha. So the moment map is essentially given by the all moment map plus a term which is the contraction of the generators of the action with the one form alpha. So it's canonically, there's a canonical formula. So the remark is that this diagram, so the morphism, the algebra morphism I wrote down here, what is it? Here, psi, has the property that this diagram involving phi commutes. And I will write it little by little. So here, I write down the method psi that we obtain from omega. I can do the same thing for well, the form, so to say, symplectic structure. So psi omega plus dA means essentially that we take the Hamiltonian vector field with respect to the new symplectic form. Yeah, the algebra bracket is twisted by the new omega. Okay. Now, so it is very well known that these two algebras are isomorphic. So a primitive of omega gives you a concrete isomorphism. This is Gauss transformation. Just means that so the vector field part remains the same in the function part. We just add the contraction. So okay, I would like to say that I can complete this to a commutative diagram. So the problem is that, well, even though the underlying spaces are the same, there is certainly no Lie algebra isomorphism between these two. So the symplectic forms are different. But, well, by introducing a moment map, we can basically look at, say, finite dimensional subalgebras here. So this is the dual of the moment map. So the dual of, yeah. Well, let's say this is the pullback. This is the pullback. Where is the moment map? I wrote this somewhere.
Yeah, I see.
So the moment map goes from M to G star. So you can take the pullback of functions and restrict it to linear functions. So that's this map here. And this map is a Lie algebra map. This corresponds exactly to having a moment map. So you can view G as a Lie subalgebra in the Poisson algebra functions with a specific embedding. So I'm going to do the same thing. The form moment map, and now this diagram commutes. So I cannot fill in an arrow here to say that it commutes, but restricting to finite dimensional subalgebras in a specific way. And okay, I'm not sure what is the best way to interpret this. Like very, very loosely speaking, maybe one could say that this algebra map that we wrote down here depends essentially only on the cohomology class of omega. But that's very loose because we have to restrict. I have to put moment maps into the picture to make such a statement. Okay, now the geometric interpretation. Of what? Of this map here. So this is related to pre-quantization. So let's assume, just for the sake of the geometric interpretation, let's suppose that omega is an integral form, or to be more precise, that with this factor we obtain its class is an integer cohomology class. So well, then it's well known that there is an S1 bundle with connection whose curvature is omega. So there exists an S1 principal bundle. Let's call it pi. So P over M. Connection. One form of the total space, one invariant. And so the connection has the right curvature. So d theta is the full gap. Let me try to make a drawing. I'm sure we will meet in a second. So if I draw M like this, then this looks like a trivial S1 bundle. Okay, so this is the pi, P, and since I have a principal S1 bundle, so the orbits of this one action will give me one S1 here, and the number 1 in the Lie algebra of circle gives me a generator of action, which I will call. So that's a vertical, and this one invariant vector field. Okay. And the connection. The role of the connection is to give you an Ehresmann connection. So a horizontal distribution. So this thing in orange is the kernel. So that allows you to lift vectors. So okay. So should I leave this? Or?
No, you can erase.
Oh, yeah. And now, well, essentially the so-called frequentization map realizes the Lie algebra morphism side of the okay. So, well, we got the Lie algebra embedding. So this is all part of the frequentization story that was developed by Suryo and Constant in the 70s. So, well, I will try to say a word about why they were doing something like this. So the principal boundary connection allows you, well, gives you a way to give you a map from functions to vector fields on the principal boundary. Such a function, you might be following, you take the Hamiltonian vector field of F, so that lives downstairs on M. Then you take the horizontal lift with respect to the connection. So if you did just this, then you wouldn't get a Lie algebra map because the connection has curvature. But it turns out that you can fix everything by adding the vertical vector field. This coefficient is just a vector function. So, okay, so the statement is this map sends the Poisson bracket to the bracket of vector fields. And well, Korsten and Suryo were interested in this because they, well, as a first step toward quantization, they wanted to construct a faithful representation of the Poisson bracket of functions here. And so an obvious representation is just take F, map it to its Hamiltonian vector field, and let that act on functions on M, say. But this map is not injective, because if you take a constant function, then its Hamiltonian vector field is 0. So to get something, an injective map, well, they had to introduce this principal bundle. And so you see F appears here. So you get injective. Okay. Step number 2, so to say, we have a Lie algebroid isomorphism between the so-called Lie algebroid, I guess. I will say a word about it. And the Lie algebroid I introduced on that record. Okay. So what is this? Well, TP is obviously just a tangent space to P. So that's its sections are just vector fields. So of course they have a bracket. here I'm just dividing everything by the derivative of this one actually. So these two things are vector bundles over M. And the algebra is isomorphic. So here again, I use the connection. If I take a tangent vector in a number, I can take the horizontal lift of the tangent vector plus that number times the vertical vector field, the generator of the action. And this turns out to be present brackets. So composing, I eventually get the map. So I have on that side. So sorry, this. So there is the quantization map. Here I'm just using the isomorphism on sections given by this, the algebraic isomorphism. So notice that both use the connection. So the quantization map, because of the lift, uses the connection, and this one too here. Well, the result turns out to be independent of the connection and is exactly the map. If we go to the computation, exactly the map that they wrote here. So these Lie algebra morphisms that you can write down for any symplectic manifold in the integral case can be interpreted as the pre-quantization map, well, upon an identification of the invariant vector fields with this. So in the symplectic case, this map has some geometric content, and so what I want to do is to extend this to higher differential forms, and what that might be a hint that there is a similar nice pre-quantization picture or a version of it, even in the higher case. So there is some literature about it, but no result that really that gives a procedure as nice as in canonical. Okay. So I will get into the general case only at the very end. So first I want to discuss the case one higher, so closed tree forms, so-called two-plectic forms. And in that case, it turns out that, well, you don't have an associated Poisson algebra or Lie algebra or something like that, but you have a more flexible notion, and you have an infinite algebra. So I want to say a word on the infinite algebras. Just to give an idea of what kind of structures these are, if you haven't seen them. Infinite algebra consists of. So basically, this is the notion you get when you take the notion of Lie algebra and allow the underlying vector space to be a graded vector space, not just a normal, usual, ordinary vector space. So graded vector space, graded by what? By the integers. So this means that I have a vector space in a direct sum decomposition indexed by the integers. And then we have, well, maps that are not just a binary map, a map with two inputs and one output, like for the algebras, will allow any number of inputs. Linear, skew, symmetric, in the graded sense. Degree at 2n minus 2 maps. So I write them like this because I have n inputs. So they take suppose tensor. So they take n elements of V and give you back an element of V. So satisfying some kind of Jacobian. Higher.
So how does this behave with respect to the gradient exactly?
Okay, so for every n, you have one of these maps that take n inputs and one output. Saying that it has degree 2 minus n means that if you plug in homogeneous elements, so elements with a well-defined degree, the result will have as degree the sum plus this number here. So let me make explicitly all that. A very, very simple example, a big example. So let's suppose our vector space is our graded vector space is just an ordinary vector space. So concentrated in degree 0. Then, well, then the only map that survives is the one for n equal to 2. Because you plug in 2 elements of degree, well, you plug in elements of degree 0. If you want the result to have degree 0, then, well, n has to be equal to 2. Then you get the algebra. So when only the first map for n equal to 1 is non-trivial, or there's a 0 with a chain complexes. Well, yeah, there are more examples, of course. Okay. So let me just mention something orally. So if I wrote down the higher Jacobi identities, they would look a bit arbitrary. In particular, there are lots of signs, very ugly. But there is a way to encode this structure by one object, and then the higher Jacobi identities just become that object squares to 0. So in words, you can, out of V, you can construct a certain co-algebra and the brackets assembled into a co-derivation of that algebra. And if it has square 0, you have an.
But this higher Jacobi is not for each n, but involves the brackets for different n.
Yes, like if I had to write them out, then of course I would have a hierarchy, and each equation would be quadratic. I mean, would have 2 brackets. So okay, so try to focus more on the geometry than on the algebra. So let me pass to the two-plectic case and say what we know there, all of which was known already 5-6 years ago. So here, Courant algebroid will appear. Well, first, just to be explicit about what I mean by two-plectic. Two-plectic form. So tree form, so not two, but tree form, which is closed and non-degenerate. So closed is clear. Non-degenerate means that contracting with a vector is an injective operation. And so this is enough. EM to wedge 2 now, Mr. M, which takes a vector contraction omega. This is injective. So in the symplectic case, here we just have Mr. M, so saying that it's injective is the same thing as saying that this is isomorphism. Here, so now the rank of this is usually larger than the rank of this.
Does this coincide with this notion of positive free forms in 6 dimensions by generalized?
So I think those satisfy this property. So this is just closed and non-degenerate. Nothing more. So these are these are also called multisymplectic forms. So if I say two-plectic, I specify the degree. And they appear in field theory, for example. And okay. And one can, like people like John Biles and his student Chris Rogers, try to see how far you can push certain constructions in symplectic geometry to this. So I'll show you some of that. And at some point things will break down. Okay. First, you can try to define Hamiltonian vector fields. Like if you write down the usual formula, you see that you cannot associate Hamiltonian vector fields to functions, but to one forms. So Hamiltonian one forms at the one forms, such that there exists some vector field, VF vector field, and we'll call it X alpha. There exists some vector field such that if you plug it into omega, you get the sign minus the alpha. So if you count degrees, you see that alpha is alpha has to have degree 1 less than omega. Sorry, 2 less than omega.
So alpha is in omega, like omega 1 or omega in your equation alpha?
So I'm taking the Hamiltonian vector field of alpha and plugging, sorry, I'm taking this vector field
for alpha in
omega 1. This will be 1 for alpha. So, well, if you try to count degrees, you'll see that it has to be 1. And okay, so one can try to define the Poisson bracket as usual. One forms. Let's take the usual formula. You take omega, and then you plug in the Hamiltonian vector fields. So now we have one slot left. So this is a well-defined operation here, but it's symmetric, obviously, but it does not satisfy the Jacobi identity. So the Jacobi identity fails. Right now, how it fails. If I take the Jacobiator, so this plus cyclic permutations, I get, well, to sign maybe, but I get d of omega with the 3 Hamiltonian vector fields. So you get, so the left hand side is the one form. Well, it turns to be out to be exact, but not 0. So the Jacobi identity holds to homotopy. And okay, so now I'll basically play the same game that I played in the symplectic case. Out of such a structure, I will associate 2 algebraic objects and say that they're related by morphism. Now, not the algebra morphism.
Right now, omega is non-degenerate in the sense that you get this injection. Does it make things better if somehow we were to say that whenever you plug in a vector, you get a non-degenerate form in the complement? Like some sort of like a even more non-degenerate than just asking for an injection.
Yeah. Well, for this story, it doesn't make a difference. So people have been considering that, but it doesn't make a difference here. Okay. So let's take the 2-plectic form. And one can associate 2 kind of objects. So the first one, due to Chris Rogers, 2009, roughly, L-infinity algebra, which I will call L-infinity and omega. So these are what he called them observables. And yeah, well, so let me give a flavor of how it looks like. So without getting into, so I will not tell you all the structures. And let's try to motivate it. So like the naive thing to do would be, well, take the Hamiltonian objects, which are one forms, with a Poisson bracket. Right? So the naive thing to do would be just to look at this. The problem is that this bracket here, which I shouldn't call Poisson bracket, so that bracket does not satisfy the Jacobi identity. So I don't get to the algebra. However, I can still put this in degree 0, so view it as an ordinary vector space. I can add one piece 1 degree lower. And so this extension, so to say, that gives me more space. And it turns out that you can put an L infinity algebra structure here, extending that bracket. So I'll be a bit sketchy about how it looks like. So this map, this is the unary map. The map with one input, one output is just the Deram differential. Then we have a map that takes two inputs here and gives an output also in degree 0. That's the bracket we define there. And then there is a trinary bracket. We do it like this. You take three inputs here, define in some way the failure of the Courant bracket to satisfy the Jacobi length.
And like because of that, like if I also look at your previous study in which you also failed to satisfy Jacobi, was there a version of Jacobi with different ways of putting the brackets that would actually be 0? Like that equation that like we do satisfy Jacobi if we don't require this symmetry, right? But use the bracket.
Yes, I think if you take if instead of defining the bracket like this, you take, what was it? Well, some formula with the lead derivative, I forgot exactly which. Then you get a Leibniz algebra. So you lose Q symmetry, but the Jacobi identity, the analog of the Jacobi identity is satisfied. All of this is work by Chris Rogers.
Select alpha beta minus select beta minus.
Well, it would be, yeah, I guess it's a Q symmetrization. So in degree 0, the bracket is just a Courant bracket, the twisted Courant bracket. Then there is a trinary bracket, which involves taking the Courant bracket and then declaring with the third section. And actually there is also a bracket that takes an input in degree -1, so a function, a section, and this. So there is one more bracket that was what there was. So the exact formula.
So the binary one is just the Dorfman or the Courant bracket. The one
yes. So this is what if you want an attempt to extend, the Courant bracket to some algebraic structure that satisfies some kind of integrability condition.
And the ternary, the Jacobi.
No, the ternary takes three sections here. Yeah, it's something like this. Well, it's Q symmetrized.
Okay.
And with a factor of, I think, -1/6. And that will come back. So, okay, again, I asked the same question. What is the relation between these two algebraic L infinity algebras, L2 algebras that I have there? And Chris Rogers in 2012 or something like that, stated that there is an L infinity embedding, an embedding of L infinity algebras of one into the other. So there exists infinity algebra embedding but let's call observables. So this includes this is the object that extends the Hamiltonian one forms into the infinity algebra associated to the Courant algebroid. Which I will just note. So you see, as the underlying graded vector spaces are not that different. So in degree -1, you have functions on both sides. Here you have some one forms, whereas here you have one forms plus vector fields. So they're not the same, but they're not so different. So now, an L infinity algebra morphism is not just a map between the underlying graded vector spaces that preserves the brackets and the nodes. So it's not just a linear map from here to here that sends the differential, the unary bracket here to the unary bracket there, and the binary bracket here to the binary bracket there. So it's not this. So there is it's a much more flexible notion. An L infinity algebra, an L infinity morphism has various components, and a way to understand this is to goes through the description of L infinity algebras in terms of this co-derivation of this, like, so if you encode all this hierarchy of brackets by just one object, which I said is a co-derivation of a certain coalgebra, one object squaring to 0, this corresponds to Jacobi identities, then from that point of view, it's very natural that you have many components. So for those of you who like the language of graded manifolds, say finite dimensional and infinity algebra is just a graded vector space with a vector field of degree 1 that commutes with itself, and vanishes at the origin. And the map between two such things is not just a map of graded vector spaces, it's a map of graded manifolds. So it doesn't have to be linear. And that gives rise to the high components.
Is this a manifestation of the fact that I can regard one forms as functions in the loop space and sections of the Courant with sections in, functions in the loop space of the cotangent, and then the projection map from the cotangent to M gives you a pullback map from functions.
Yeah. So we haven't checked that. So I don't think that. So this contains more information. So one could try to compare this diagram to, this map to what you would get by taking loop spaces on both sides. So by doing so, the form, you transgress the 3 form to a 2 form, right? So you're in the 2 form setting. So you would have a similar map at the level of 2 forms, and then you would try to fit everything in one diagram. But this contains more information. You lose information.
The potentials for this encoded in this.
Yeah.
So I can understand that Nepal infinity algebra is more general, but like this, because right now you have two that look very much the same, like they have the same sort of brackets in the same degrees type of thing, right?
I wouldn't say they have the same sort of brackets. The underlying spaces look quite the same. Okay. So I'm going to write down the components in there just to. So. Components. And the first one, formally. The first one, sorry. So each of these two infinity algebras has 2 components, right? Degree -1 and 0. So from degree -1 to degree -1, you just have the identity. So this is the identity. And from degree 0, 1 forms. So we have to set the algebroids. And this is exactly the same formula that I have. Again, alpha goes to alpha Newton. And then there is a second component, which takes as input 2 Hamiltonian 1 forms and as output function. So you take 1 forms, the function. So you take the Hamiltonian vector fields, contract them with other 1 forms, with other 1 form. So this gives a function, it's symmetric. So the formula themselves, I guess, are not so important. So my main point is you don't just have one linear map, you have many components. So notice, so this here is just the skew-symmetric pairing of 2 things like this. So pairing with a minus. So this is where I wanted to use the slides. And so actually I also handwritten notes. So I guess I'll use those.
You are the chair.
Yeah, well, we have to continue, right?
Yeah.
Se dio la luz en todo el edificio.
Entonces,
No, ahora hace un momento, ¿no?
La cafetería no hay.
I mean, you can show them in a laptop. Like
if you're comfortable with using your notes, on the blackboard.
So you have no big screen here, right? I mean,
yeah, no, we can't.
Yeah, but it's projector.
Yeah, no.
Marco, can I ask you quickly, while you were raising, this omega can also be thought of as one of these higher Dirac structures, right?
Yes, sure.
And there must be some sort of admissible set of, just as for Dirac structure, there are admissible functions that we have a brackets Is this related to this Hamiltonian one?
Well, you have a notion of admissible form for these higher structures, what are they are? I mean, what are definition exactly? And yeah, in the bracket. Well, yeah, we do, and you can define skew symmetric bracket.
And it's the same thing. Is this
This is a special case. Yeah, closeness is important here. I mean, closeness. So closeness is important for the fact that you get an infinity algebra structure, that you can extend this bracket that fails to satisfy Jacobi to an infinity bracket. Yeah, it's not essential. I agree, it's not essential. You can repeat the whole story without non-degeneracy. Yeah, then you have to. So without non-degeneracy, you might have, like if you have a
non-unique.
exactly, you have to keep track of the Hamiltonian vector fields. So you enlarge your space to include all possible choices of Hamiltonian vector fields. So, okay, I wanted to use slides for the higher case. Formula at least to see, for you to see. And well, so I will not, so I have something like 15 minutes.
Yeah, but you can use a bit more time if you need. So given the circumstances,
I'll try to stick to that.
although the room is getting warmer because air conditioning.
I'll try to stick
Say
to
dentro del campo.
So in my practical form, well, just you can guess what it is by now. It's a closed, non-degenerate in the same sense that I showed there. Two form, it was one form. Classes of examples in general include volume forms. And so exactly as the cotangent bundle of any manifold is a classical example of symplectic manifold, exactly by the same procedure, wedge n of any cotangent bundle as an exact. So again, out of such an object, you again get two algebraic things. I will not describe them in detail. So in any infinity algebra, the same symbol, and omega, the underlying vector space is Hamiltonian now n-1 forms. And in lower degrees, well, you have all differential forms of lower degrees. n-2 forms, degree -1, and -3 forms, 1 degree lower, etc. And well, you can associate, you can get something called higher Courant algebroid. M plus wedge. Again, with the bracket, I should write it here. With the bracket twisted by omega. So the first place where I read about this was in Markov algebroids, essentially. There's a section. So you notice that the usual formula for the Courant bracket or Dorfman bracket doesn't use the fact that alpha and beta there are one forms. They can be forms of any degree. And again, so one can extend the theorem of Reutemann and Weinstein to get inner infinite algebra. Name for it. Underlying vector space is completely analog to earlier, like in degree 0. Maybe I should write it. In degree 0 sections of now Tm plus wedge n-1 plus m. So we have pairs consisting of vector fields and n-1 forms, and here just any negative degrees to just differential forms of all. And so the infinity algebra. So the multi brackets. this infinite algebra have Bernoulli numbers. Coefficients. So what I mean is that the higher brackets are given by some formula involving Cartan calculus, like Dirli derivatives, contractions, and so on. But in front of them, the Bernoulli numbers. So the 1/6 that was appearing in the White and Rodenberg algebra, that's one of the numbers.
And this is essential for the actions satisfied.
So
why do this?
It's sufficient, yes. So this allows for the higher Jacobi identities to be satisfied. So this is work, well, essentially it's work of Getzler. For the preprint 10 years ago, I discovered that it was never published because, well, Damian Kalak made the remark that the result follows from previous work of Fiorenza and Manetti. So I think Getzler had exactly this case in mind, algebroids, but he didn't write anything about it in the paper. So, well, I wrote it down explicitly a few months later. Okay. So the main result.
Yeah.
So
It's coming back. Okay.
let's try that one.
Sí.
You say what iterations is A and B?
I haven't said that yet. Okay. Well, in analogy to what is
Okay, so there is a priori there are like two different examples. We're going to relate.
yes. Yeah. So I don't know, from a naive point of view, these are just two kind of algebraic structures you can associate to a closed, or say non-degenerate differential.
The Courant algebra only has like two brackets, right? Or
No. It has yeah.
Because in degree 2 it just 3 brackets, but if it's high degree forms in Courant algebra, it's also more.
Yeah. So this has pieces that start in degree 0, the underlying vector space, and end in degree -n+1. So since you have more degrees in this in the underlying vector space, greater vector space, you can have more brackets. Well, you can associate two structures in analogy to what I did earlier. So the infinite algebra observables. So these are the higher brackets. They're very simple. All the entries have to be in degree 0. So these alphas are all -1 forms. And then, so we'll very quickly skim through the brackets for the infinite algebra associated to the higher Courant algebroid. This is the underlying complex vector space. The unary map is very simple. It's just the Derived differential. So this is not for you really to read, just to have a rough idea. So the E's are concentrated in degree 0. So they are sections of the higher Courant algebroid, and the Xi's have lower degree. So you get non-zero brackets only if all the entries have degree 0 except maybe 1. That's not that bad. And you see there's some numbers. Bernoulli numbers appearing here. These are the higher brackets, and so the capital B's are the Bernoulli numbers, and the lowercase b's are the Bernoulli numbers sometimes, some numerical constant, and they appear as coefficients. So this was just to give, don't try to read all the formula, just to give an idea. Okay, so this is the main statement. So that's what I was working toward. That for every n, well, we realize an embedding of the infinite algebra observables to the infinity algebra associated to the higher Courant algebroid, twisted by omega. And we can also give explicit formulae for them, which are not so bad. Like the unary map, so the analog of this looks exactly like the previous case. The question was, how do the higher components look like? Well, there is a nice formula that you can write down, and it's the same formula for all higher k's, 2, 3, 4. So the Bernoulli numbers appear as coefficients here. And yeah, so the answer is actually, well, to me, surprisingly simple. So you could, a posteriori, I think we could have even guessed it. And well, okay. Again, about the motivation, well, the work we did is essentially algebraic, just this theorem. So the hope is that this can shed some light on what happens when omega is integral, and maybe there is some kind of pre-quantization procedure behind. And so there are, as I said, in the literature, there are some versions for n equal to 2 at least of pre-quantizing the symplectic structure. And well, the fact that one should recover this morphism is maybe a test to check if this procedure are well behaved. Working. So this does not work.
It's the last slide.
No. Oh. I remember a couple of days ago. Okay, the case n equal to 2 is due to Rogers, as I said, and actually two physicists. I works too much. So and actually the existence of this morphism was predicted well by two physicists who gave a proof that it's not really constructive and well, in some parts just say this goes analogously to the previous case, but they didn't give any formula. At least I can say that we are the first to use a formula. So they're like the pentagonal diagram with the moment maps keeps holding us in this case. So I have 2 minutes. So let me give you a flavor of how one can try to prove this. So if you try to do things by hand, so at the end one just has to show that this sequence of maps satisfy the axioms of L infinity morphism, which I didn't write down, but they're essentially the fact that they preserve the multi-brackets in a very loose sense, not in else. So in principle, it's loss of Cartan calculus, but it becomes unmanageable. And
the coalgebra picture doesn't help.
Sorry?
The coalgebra picture.
Yeah, it does help. So I should also mention that most of the work was done by my student, Anton. Most of the computations, and also he understood what was an approach that is better than just Cartan calculus. Okay. So step 1, well, that was actually known earlier too. So we have these two spaces, the L infinity algebra of observables here, the other one here. And so there is a more or less obvious map, actually step psi 1, that identifies my first L infinity algebra with a subspace of the second, which is actually an L infinity subalgebra. So on this thing that I call A, never mind how it looks exactly, I have 2 L infinity algebra structures, one obtained from the observables under this linear isomorphism, and the other one restricting the one of the higher Courant. So now we just have one underlying vector space on which we have to work. So that's good. And the strategy is the following. So this is a general fact. So if I give you any arbitrary linear map, so never mind the degree shift by 1. That's the technicality. So this is the symmetric tensor power of A. So if you give me any degree 0 linear map from here to here, that can be extended to a coderivation of this, which is a coalgebra. This is an algebraic structure. And when you exponentiate the coderivation, you get an automorphism. Exactly like for algebras, if you exponentiate a derivation, you get an automorphism of the algebra. Okay, and once you have an automorphism, well, you can do lots of things because an L infinity algebra on A is the same thing as a coderivation here squaring to 0. So if you have an automorphism, you can take whatever objects you have on this side and take it to the other side to get an object with the same properties. So I take the coderivation encoding the L infinity algebra structure in observables, and I bring it to the other side. And okay, so I get a different coderivation, which is, however, isomorphic by this map to the previous one. So translating to the world of L infinity algebras, that means that we get a new L infinity algebra here, which is L infinity isomorphic to the one given by the observables. And now, if I can guess a degree 0 linear map like this, which sends the L infinity algebra on the observables to the one on coming from the higher Courant algebroid, I'm done. So mostly the work was trying to figure out what this. So this is the last slide, apart from the references. So we make an ansatz. So this symbol here is, well, this symbol here is just a skew-symmetric pairing on my high-Courant algebra. So it's inserting vectors into differential forms, skew-symmetrized. So you have to interpret that a little bit to extend it to a map defined on A and then on higher symmetric powers. And there is a notion of composition or product on maps from here to here, because maps from here to here, well, degree 0, correspond to co-derivations, and co-derivations can be composed. So this is kind of composition. That is what this power means. So we take basically a power series, these things with some coefficients. And so remember that the binary, well, the second component in Chris Rogers' map for then equal to 2Ks was given by the skew-symmetric. Suggest to look at something like this. And then what we carry out the computation basically, well, in a symbolic way, if you want, not plugging in elements. We compare co-derivations, if you want, or maps from here to here, linear maps from here to here. And then, well, we see that certain coefficients are such that the infinite algebra we obtain by pushing forward is exactly the one we want, the one coming from the higher Courant algebra, right? And and writing down things explicitly, we get like the coefficients explicitly, we got the Bernoulli numbers that appear here. And that's it.
Thanks, Marco. So any comments?
I have a question about, this generating function of the Bernoulli numbers that you wrote down. Does it appear in this way that you mentioned at the end, like taking X to be C, the co-derivation in your solution? You see what I tried?
No, which X? Which X are you talking about?
No, so that's an analytic function, X divided by e to the X minus 1. So you could, instead of X, plug in an operator like this one. Is that the shape of the solution or something?
I don't know. We didn't think along those lines. And so these numbers are not exactly the Bernoulli numbers.
But the Bernoulli numbers appear in the solution, right, of the morphism.
Yeah, because so this.
So it could be that the inverse, the multiplicative inverse of that is why they appear.
Maybe, I don't know. Like we just did a straightforward computation to check that things match.
Chris, a vague question. Is it possible to rid of these brackets out of some sort of extended loop space where you consider maps from a d-dimensional manifold to your target, but this has boundary, and the boundaries have boundaries, and the boundaries have boundaries, and then you apply iteratively Stokes to get what is E.
So I'm doing in this way, you would want to recover what?
Yeah, for example, in the first case, in this two-plectic case, what you get as once you do the Poisson bracket of 2 one forms thought of as functions in the loop space is d of a function. If you integrate over a circle, this is 0, right? But now if you have an interval, you will read that function from a Stokes theorem. So I wonder if you can do this iteratively for in the space of maps from some d-dimensional space to your target manifold. Thought of your whatever n-plectic structure as a symplectic structure on the space of on this loop space, higher loop space, and then read all these higher brackets out of that abstraction, like going inner and inner into the star.
So now you're talking only about this, right? You're not talking about the morphism. You're just talking about the infinite algebra associated with what I call observables.
Yeah.
So yeah, I never thought that deep. So I can tell you that this object behaves well with respect to transgression. And but yeah, I did some computations only involving the loop space, so no boundaries.
very basic question. Your theorem is that you have an analytic algebra embedding. I guess this means that on cohomology you have injections.
No, embedding really means injecting. So by embedding, I mean that the unary map, so the first component, the one that takes one vector there and gives one vector here, is injective, which was quite clear from the formula because you have an alpha here and x here. That's all. So that doesn't mean that in cohomology you get an injective map. Sorry, in principle. Now here the differentials. So the differentials are both the same on both sides, the Deram differential. So in this case, you do get an isomorphism in cohomology.
So I mean, when you call one side the observables, right, I assume that it's from some kind of a theory, a physics theory.
Yeah. So well, it can have
from an algebra.
True. So if I remember correctly, so the justification that Chris Rogers gives for this name is the fact that out of these one forms, so if you look at loops maps from S1 into your space with the three forms, say, and then you can associate to an observable, you can associate a number, because the observable is the one form, and so you can integrate it. You can put it back to the circle and integrate it. That's, I think, the reason.
So it's a sigma model.
Yeah.
Into a higher Courant algebra. Or at least it's like, there were some talks earlier this week about U1 gerbs. So presumably there's a U1 gerb, N gerb, and then you're looking at a sigma model of maps from n-dimensional space to that target.
I'm not sure, but so you're still talking all about this, right?
Yeah.
I don't know. So I know that U1 gerbs appear. So in work by Gabriel Sevestre, 2009, I think. So he and then Tilman Boltzbacher gave a version of pre-quantization for two-plectic manifolds, which involves indeed a certain an S1 gerb, but infinite dimensional. So
but your target, like the target infinity algebra, is supposed to be the gauge symmetry algebra of that U1 gerb.
In principle, so in analogy to what happens for S1 principal bundles, yes. But so I certainly don't know how to realize it in this way. So in other words, so when I was talking about the symplectic case, I said this map arises as the composition in the integral case of two things, the pre-quantization map, and a more or less obvious identification between S1 invariant vector fields in the S1 bundle and certain sections of the algebroid. So that part, I personally have no idea how it should work in higher ends.
I think regarding the calling the things on the left hand side observables, I think that isn't that also motivated by geometric quantization, where in the symplectic case you would just have functions, and then using the pre-quantum line bundle and the connection on there, you get a Lie algebra structure on the functions, so then you interpret the functions as classically the functions are the observables, and then in the quantized theory with that Lie bracket, you interpret that as the quantized and therefore non-commutative version of that algebra of classical observables. And I think here the idea is just that the observables, well, what do you replace the functions and the manifold with? And so you need something that you can sort of induce or go from a commutative and in this case differential graded algebra structure on the forms to something non-commutative, to a higher Lie algebra structure, just analogous to the geometric quantization case, which is then I think exactly what happens in the left-hand side. I think that's how or why Chris Rogers and John Byers called it observables, motivated by the geometric quantization.
That's the same as what I think Mario and I were just saying. Because if you have a sigma model dimension 1, let's say, with So the boundary would just be a point. You're mapping a
Right.
point into a symplectic manifold, and the observables are functions. If it was a two-dimensional sigma model, the boundary would be a circle. The observables would be one point.
Okay. Right. Yeah. And then
Go ahead.
you mentioned the work of Sylvester and Wurzbach, and they show. Maybe I'm just a bit fuzzy on what exactly they do, but so you prove that there is an embedding of L-infinity algebras, and they show that there is some sort of quasi-isomorphism of L-infinity algebras.
Yes, that's right. So their pre-quantization map is an L-infinity morphism, but it's not injective. It's only injective in cohomology. And so actually I was talking to him about this yesterday. And yeah, so like their construction, I mean, like, so the construction cannot be used to say, we compose the construction with some identification between vector fields on this U1 germ and sections of this and elements of this L-infinity algebra associated to the Courant algebroid to recover that this L-infinity map. So one has to change a few things.
So no more comments. Let's thank. Oh, sorry, Mario. Go ahead.
Is there a notion of deformation quantization for this?
Let me think before. Not that I know of.
So,